Hello, I'm Thrishantha Nanayakkara. I'm an associate professor of design engineering and robotics at Imperial College London. Today I'm going to talk about behavioral lensing, a phenomenon we observe in manual palpation. So when you go to a GP, for example, you will see a repertoire of actions they take when they want to observe or feel something in your abdomen. So the question is, why do they do this kind of actions when they want to perceive something? So they would take these actions like percussion, bimanual examination, and then control the stiffness of the fingers and the shape of the fingers when they want to perceive. So this active process of gaining haptic information and auditory information and visual information leads to a sharper perception of a random variable they want to examine. For example, if it is the depth of a nodule or the distance to the edge of the liver, for example, you can feel the same variable in a haptic domain, and then there's a haptic noise, and then the visual domain and visual noise, and auditory noise. So when you do a Bayesian integration, what you get is a sharper posterior starting from some likelihood functions. So the interesting thing is we observe that the brain takes at least two different pathways to condition this perception. So one is an internal pathway where the brain conditions the body, the posture and the stiffness of the body when you want to feel something. And then the outer pathway where it controls motion and force. So if we say zeta is the vector of internal parameters and then phi is the vector of behavioral variables, you can have various combinations between these two to condition the noise distribution of some mode of perception. So what this leads to is a conditioned perception where so you condition the likelihood functions that will in turn change the posterior shape of the distribution. So for example, when you ride a bicycle on a bumpy terrain, the brain would take an internal control action to get the person to stand up, stand with the bent knees, and then the condition the stiffness and the viscosity of the joint, which is a zeta variable, and then a phi is a riding behavior. And then that way, the brain doesn't have to deal with all the complex bumpiness of the terrain. So the terrain bumpiness will be taken care of by the body itself, and then the brain can focus on the riding function. So this is important because we cannot really separate perception and action because most of the sensors are part of the muscles themselves. So the good news is that you can take action to condition the way these sensors are going to feel, right? So for example, if you have a probability distribution of a random variable, which is d, yes, the d is the random variable, and then which is a condition distribution of zeta 0 and phi 0, and then if it is, let's say, this dotted broad distribution, and if you can move that internal parameter to zeta and then the behavior to phi, right, you have a new conditioned body like the stiffness of the fingers, and you have a new behavior. If that new distribution is this light blue distribution, which is sharper, we call it information gain. So the clarity of the information improved, and then we can quantify that by Kullback-Leibler divergence. So, what that means is like, so by taking actions in internal conditioning and outer movement and force, you can change the sharpness of perception. So we call this behavioral lensing. So we lens, magnify the effect or sharpen the effect by taking actions. So we have tested this phenomenon in robotic fingers. For example, in this case, we have a robotic finger where we can control the stiffness, and then we explore to estimate the depth of a nodule in a soft tissue. So what we see is that by controlling the stiffness of the finger, the perception at a tendon level, like at the base level, changes, right? So there's no kinematic difference, like it is just the internal stiffness that changes, and that way when you sweep on a soft tissue, the tendon sensor, which is a force sensor to represent the tendon organ, the prominence changes. So if you do another trial, what we see with the different stiffness, yeah, the prominence changes, right, with the stiffness. So we have seen this in various exploration behaviors, and then we can make sense of why the humans are also doing the same thing, just to change the sharpness of perception of a random variable. We can control the body stiffness. What that means is, like, so when you take a lot of data, you see, sorry, so you see that by controlling the stiffness of the finger, the shape of the likelihood function changes. The likelihood function is the probability of perceiving something given the data, right? What you really want to know is the data given the perception, right? So if you want to know the depth of a nodule given how you feel, so you can formulate that as a Bayesian inferencing problem of likelihood function and prior distribution. So what you can do is, like, rather than doing a passive Bayesian integration with a fixed likelihood function, you can condition the likelihood function itself to converge faster. So what we see here is, like by conditioning this likelihood function, you can change the shape of the likelihood function by having the stiffness, and then it converges the posterior to a sharp distribution starting from a flat distribution in just 4 trials. So we have seen this phenomenon in the behavioral domain too, right? So in the previous slide, I showed how it changes with the stiffness of the finger, which is internal conditioning. This is external conditioning, which is behavioral conditioning. So we see human subjects, when they explore a soft tissue, they do a wiggly movement, and then this wiggly movement can be characterized by getting data. So we saw that this is a sinusoidal lateral force with 20 hertz, and then a second order autoregressive normal force. So once we know these models, then we can export it to a robotic finger, and then we can implement that to see what they feel, right? So we feel what they feel through a robotic finger. What we see is that, so this 0 is the baseline, which is what you feel as the nodule when you just press without this wiggly movement. And then when you have this wiggly movement, what happens is, if there is a nodule at certain depth, which is 3 millimeter depth, you feel the nodule harder than what it is. And then if there's no nodule, you feel the tissue softer than what it is. So this is something like a magnification of the effect. What it is the 0, and then you feel magnified than what it is when you have the right behavior. So that means you can have right behavior or the right stiffness of the fingers to clarity, gain clarity of perception. So this is what we call behavioral lensing of perception. Yeah, this work was done as part of the EPSRC funded RoboPatient project. And then these are my collaborators and lab mates at Imperial College, Cambridge University, and Oxford. Thank you.